Okay, in this chapter so far we've talked about the relationships between logical sentences in several ways. For example, the equivalence between two sentences, the entailment of one sentence by another, or entailment by a set of sentences, and also consistency between two sentences. But let me move forward here and explain some theorems and then wrap it up in the end. So the equivalence theorem states this: a sentence phi and a sentence I are logically equivalent if and only if the logic sentence phi biconditionally implies psi is valid. Okay, that's dense and difficult, so let's use an example to pick it apart. Let's define our two sentences, phi, which is the negation of the disjunction of P and Q, or not P or Q, and psi, which is the conjunction of the two negations, or not P and not Q. All right, those are our two sentences. We're going to now analyze this sentence, which is the biconditional implication phi biconditionally implies psi. Try to pick apart what this theorem is saying. And of course, to do that, I'm going to use a truth table, because the truth table always has all the information we need, but we need to interpret it. So let's start off by looking at the two sentences that we have. We have not P or Q, and we have not P and not Q. All right. First thing you notice is their two truth columns are identical, and we already learned that that means that the two sentences are logically equivalent. But how does this sentence come into play? What's this all about? What's that biconditional implication? Well, let's take a look. When we look at the implication going both ways, that is to say, phi implies psi. How can phi imply psi be unsatisfied, or when will that ever be false? We already learned in implications that the only way for that to be false is if the antecedent is true while the consequent is false. In other words, there has to be a true here and a false here to make this sentence false. Well, that never happens, because there's never a true here followed by a false here, because, well, they're always identical. So there's never one value here and another value there. So if these are identical truth columns, then this implication must be valid, which, as you can see from the truth table, it is. The same exact argument holds going the other direction, just looking at psi implies phi. This can never be true while that's false, mostly because, well, they're identical. Okay, so what we're seeing here is that the idea of saying that those are identical is the same idea as saying that the implication both ways has to be true for every truth assignment. And remember, this biconditional implication is the conjunction of those two implications. In other words, it's saying, does the implication hold both ways? Is it phi implies psi and psi implies phi? So when is this true? Whenever both of those are true simultaneously, which, by the way, is every case. So that means that this biconditional implication phi implies psi is satisfied for all the truth assignments. That is to say, it's true for every truth assignment, which means it's a valid sentence. So what we're saying here is, if phi biconditionally implies psi is a valid sentence, that phi and psi are logically equivalent sentences. To be clear, I haven't proven that. What I've done is try to illustrate it and give a simple, straightforward example. So the equivalence theorem is saying, if you want to talk meta-level discussion about two sentences, that is to say, oh, phi is logically equivalent to psi, that itself is not a logical sentence, at least not the kind that fits in our definition in our world. We need a sentence like this right here. Now this is a logical sentence. It's a biconditional implication. And so what this is doing is giving us a way to put the language, the meta language of comparing two sentences, into the logical language of seeing, is this biconditional implication valid? And what we're asserting is, if it's valid, then those two are logically equivalent. So it's turning the meta level sentence, phi is logically equivalent to psi, into a logic sentence of phi biconditionally implies psi is valid. Let's look at the deduction theorem. What does the deduction theorem say? Well, it says a sentence phi logically entails psi if and only if the logic sentence phi implies psi is valid. Okay, let's take a look at this. Okay, let's look at two logical sentences. That is to say, P and Q, P or Q, the disjunction and the conjunction. Does the conjunction imply the disjunction? Well, I would argue that's almost trivial. So what we're saying is, when this is true, does it guarantee that this is true? Well, if both of them are true, then it guarantees that at least one of them is true. I mean, that almost seems trivial. And yet, it's an example that I can use. So now I want to focus on this sentence, this logical sentence. Because up until now, I was not talking in logical sentence. I was referring to logical sentence. I was saying this sentence is logically equivalent to this sentence. And I was saying, oh, let's think about it. If both of those are true, then that tells me that at least one of them is true. I was appealing to your kind of meta-level thinking. But here I'm literally defining a logic sentence, an implication. So let's use the truth table to build the implication truth values. We ask ourselves, okay, if phi implies psi, when is that going to be false? Well, that will be false anytime the antecedent is true, but the consequent is false. When is the antecedent true? Well, only once, actually. And is the consequent false there? No, it is not. So every single time phi implies psi is true, because there's never a case where phi is true but psi is false. In other words, never a case where the antecedent is true and the consequent is false. So that means the implication is always true. So notice that phi entails psi. What do I mean by entails? Oh, every time this is true, that's also true. Also notice that phi implies psi is valid. Yes, it certainly is. That means true for every truth assignment. Whoops. And so what we're asserting here is, in the deduction theorem, that making the meta-level commentary about these two sentences, as in phi is logically entails psi, is equivalent to saying this logic sentence is valid. So we've taken it from a meta-level discussion to analyzing a logic sentence. Let's look at the unsatisfiability theorem. So a set of sentences delta entails a logic sentence phi, if and only if the set of sentences combining delta and the negation of phi is unsatisfiable. Okay, we've got to disentangle this. So I'm going to use an example, one that we're familiar with. So let's set up a set of sentences, phi 1 and phi 2. That's P implies Q and Q implies R. And then our third sentence, psi, P implies R. To some people, it's obvious that if P implies Q and Q implies R in turn, then P implies R. Well, warning here. Sometimes things that are obvious to us on our heads are actually not correct. I mean, let's face it, myself, I'm susceptible to this, as is every human. Sometimes we have logical fallacies that make things that are not correct seem obvious. That's what we're working to undo here. So in this case, phi implies Q and Q implies R. Some people think P implies R is obvious from that. Well, it happens to be true. What we're saying is delta entails psi. And we proved that, if you remember previously, using a truth table. But I'm going to prove it here, or I'm going to not prove, but pick apart using this example what the unsatisfiability theorem is saying. What it's saying is make a new set of sentences. And the new set of sentences will consist of the original two followed by the negation of the sentence that you're trying to entail, or that you are proposing these to entail. And what we're saying is this: if there's ever a case where these two are true and the negation is true, then it would mean that these two do not entail that. Because entailment means every time these two are true, this has to be true. True means true here. So if that's the case, true can never mean true here, because remember, this is the negation of that guy right there. Let's put in the sentences. Now let's look at the truth table. I'm going to build the truth table slowly, but we've already built this truth table before. So here's the truth table for P implies Q, Q implies R, followed by P implies R. I built this truth table before. Now I'm going to change it slightly by having the negation of psi. And to create the negation of psi is simple. I know it's simple. I know you know this, but I want to point it out to my students. All I do is take every value here and reverse it, or negate it. So trues become falses and false become true, and so on, all down the line. So it's very easy to create that. And in my next truth table, I'm just going to eliminate this column. And now what I have here is this set of sentences, what I have called omega. There's omega, this set of sentences right there. Right there. And what we want to know here is there ever a case, a set of truth assignments, where all three of those are true simultaneously? And if you step through them, you can easily see there's never such a case. Okay, so because those three sentences together, that set, omega, of sentences, never has three satisfied sentences simultaneously, that means the set is unsatisfiable. Because no set of truth assignments satisfies omega. It's unsatisfiable. This means that we can check for entailment by checking for unsatisfiability. Okay. I hope that was helpful. Let me take a step back and try to say it clearly. If we are asserting that these two entail this, that is to say, phi 1 and phi 2 entail psi. If that's the case, that means every time those two are true, this one also has to be true. And what that means is there can never be a time when these two are true and its negation, the negation of this, is true. Those can't be true with the negation here being true, because that would be the same as saying these two are false and that, these two are true and that's false. And entailment means every time these are true, that has to be true. Let's talk about the consistency theorem. By the way, I just want to say one other thing. It seems so clear to me, but I also realize that as I explain it, sometimes I say things that make it seem unclear to you. Be aware that's how your students will feel. And that this is not easy to understand in the first run-through. And it will take not only explaining it again, but working with sets of worlds and problems over and over again before they become familiar and confident with these words and these thoughts. I really would like to encourage you to help your students increase their tolerance for ambiguity. Because when a student, or any human for that matter, is like confused and fuzzy about a concept, then their brain is screaming, please stop, I just don't understand this, and I'm being overwhelmed by ideas that I don't understand. I understand that. I get it. I feel that way myself. Okay, so I'm going to talk about the consistency theorem. A sentence phi is logically consistent with a sentence psi if and only if the logical sentence phi and psi is satisfiable. Think about that. Logically consistent means there's at least one truth assignment that makes them both true or both satisfied at the same time. And that's what we mean by satisfying the conjunction. They're both true, at least for one truth assignment. So this one seems a little more obvious to me. I'm not sure. Let's use an example nonetheless. Take our two sentences, phi and psi, the conjunction and the disjunction. So I think what we're saying is they're logically consistent if there's at least one truth assignment for P and Q that make both of those sentences true at the same time. And I would say there is one, namely that P and Q are both true. If P and Q are both true, then phi is true. And also, psi is true. Another way to say that is, let's make the conjunction of the two sentences, let's say phi and psi together, and ask ourselves, is there at least one truth assignment that this satisfies this sentence? Well, there's one right there. It's super simple once you look at the truth table. Is there at least one truth assignment that makes this conjunction true? Truth table says yes. Truth tables are super simple ideas that help us a lot. That's why I make so many of them. We can prove consistency here by checking satisfiability. In other words, looking at the truth table and saying, is there at least one case that makes the conjunction true? Satisfiability is provable using a single case of a truth assignment. That's an important thing. You don't have to prove all the cases. You don't even have to prove most of the cases. You just have to prove one case, and that's it. So, okay, this talk about theorems has been really abstract and difficult. But I do want to close it out by saying the logical properties and the relationships between logical sentences are meta level. They are things that we assert as we think about sentences, but they are not logical sentences themselves. Okay, what does that mean? To confirm the equivalence of two sentences, we say, oh, is psi equivalent to lambda? We're talking about two sentences, but we're not making a logic sentence. We're saying psi is equivalent to lambda. There is no is equivalent in our logic semantics. There's no function for that. But there is a functional for the biconditional implication. And so what we've shown here is, using the equivalence theorem, is that if you can show that this sentence is valid, that's equivalent, or that's the same thing as saying the two sentences are logically equivalent. To confirm a sentence entails another, what do you have to do? Show that phi implies psi is a valid sentence. If that's the case, then that means phi entails psi. To confirm a set of sentences logically entails a sentence, what do you have to do? You have to create a new set, that is, take the original set and add to it the negation of the entailed sentence. And if that is unsatisfiable, then this set entails phi. To confirm two sentences are consistent, it's actually pretty simple, or at least I think it is, if the conjunction of the two sentences is satisfiable. Okay, so here we've gone from using meta language about the logical sentences. We can now implicitly express those logical relationships between sentences using our formal logic language, substituting in the corresponding logical sentences. You want to talk about equivalence? Here's the logical sentence to talk about. You want to talk about entailment of one sentence by another? Talk about this sentence. If you want to talk about sentences, a set of sentences entailing another sentence, then make a new set of sentences and see if it's unsatisfiable. You want to confirm two sentences are consistent? Find out if the conjunction of those sentences is satisfiable. So what we've done is we've taken the meta-level talk about logical sentences and turned it into logical sentences. That is the only way that we're going to be able to deal with proofs rigorously.